Welcome to the deep dive. Today we're going right back to a really pivotal moment, looking at the paper that basically gave us CLIP.
That's right. OpenAI's learning transferable visual models from natural language supervision. It sounds academic, but wow, did it change things?
Absolutely. Because before CLIP, AI vision felt very constrained. You had these models trained on, say, ImageNet.
Right, with its 1,000 fixed categories, a dog, a cat, a specific kind of car.
Exactly. You had to label everything meticulously. Cat, dog, traffic light,
Yeah.
all predefined. The AI knew only what was in that training set box.
And that was the bottleneck, wasn't it? If you showed it something outside those categories, maybe, I don't know, a corroded copper pipe or something specific.
It just wouldn't know. It lacked generality. CLIP basically smashed that box open.
By using the messy, wild internet. Images and the text people naturally wrote alongside them.
Hundreds of millions of pairs. That was the first, aha moment, wasn't it? Just realizing you could use all that natural language floating around as supervision, forget the painstaking labels.
Yeah, swap human labeling effort for, well, internet scale data. And the key measure of success they aimed for was zero-shot transfer. Can the model understand concepts it wasn't explicitly trained on?
So let's put a number on that scale first because it's kind of staggering.
It really is. They put together this data set called WIT, Web Image Text, and it had 400 million image text pairs just scraped from the web.
400 million,
Yeah.
okay. And dealing with that much noisy, unstructured data, you couldn't just use the old methods, right? It would take forever.
Exactly. Computationally impossible with the older approaches. They needed something new, something way more efficient.
So what did they try first? Because they didn't land on CLIP straight away, did they?
No. The intuitive first steps were things people were already exploring, like trying to predict the exact caption for an image word by word.
Right, like the vertex approach, using a big language model, a transformer maybe.
Yeah, or even simpler things like just predicting the key nouns or adjectives in the text. Seemed logical.
But that generative approach, predicting the exact text, why didn't that scale up?
It just wasn't efficient enough. Generating precise language sequence by sequence is computationally heavy.
How much slower are we talking?
The paper actually quantifies this. They found that a transformer language model trying to predict the caption learned the visual side of things about 3 times slower for zero-shot tasks than a much simpler model just predicting a bag of words from the caption.
Wow, 3 times slower. So the complexity of language generation was actually getting in the way of learning the vision part quickly.
Precisely. The overhead was just too much for that massive scale.
Okay, so this is the crucial pivot point. They ditched the idea of generating a text and switched to something much, much simpler. Just asking, does this text go with this image? Yes or no?
Exactly. That's the core idea behind CLIP contrastive language image pre-training. It's not about generation, it's about association, matching.
And how much faster did that make for you?
That shift from the predictive generative model to this contrastive one gave them another 4-fold efficiency improvement.
4 times faster again.
Yeah, add that to the previous gains, and suddenly training on 400 million web pairs becomes, actually feasible within a reasonable time frame and budget. They traded that sort of perfect caption generation for sheer speed and breadth.
Okay, so explain this contrastive matching game a bit more. You mentioned an n-by-n grid earlier. How does that work? Let's keep it simple first for someone trying to connect, pixels and words.
Right. So imagine you grab a batch of data, say 32 images, and their 32 corresponding captions. That's your n.
Okay, 32 pairs.
Within that batch, you have 32 correct pairings. Image 1 goes with text 1, image 2 with text 2, and so on.
Makes sense.
But you could potentially pair any image with any text in that batch, right? So that gives you 32 times 32, which is 124 possible pairs.
Okay. Most of which are wrong.
Exactly. 24 minus the 32 correct ones leaves you with 992 incorrect pairs just within that one small batch.
So the model's job isn't to describe the picture.
Nope. Its job is simply to learn to score the 32 correct pairings really high and the 992 incorrect pairings really, really low. It learns to contrast the correct matches against all the incorrect noise pairings.
That does sound much simpler than writing a whole sentence. But how does it compare an image and text? They're fundamentally different types of data.
That's where the encoders come in. You have 2 main parts. an image encoder and a text encoder.
Okay.
And you train them together jointly. The goal is to make them learn a shared language, a common space. We call it a multimodal embedding space.
Multimodal embedding space.
Right. The image encoder takes the pixels and spits out a vector, a list of numbers. The text encoder takes the words and also spits out a vector of the same size.
And in this shared space.
If the image is, say, a picture of a cat and the text is a photo of a cat, their vectors should end up pointing in very similar directions. They should be close together.
But if the text is a photo of a bicycle,
Then those two vectors, the cat image vector and the bicycle text vector, need to be pushed far apart, different directions.
okay, so proximity for matches, distance for mismatches. How do you actually, mathematically enforce that? What's the mechanism?
The core tool is cosine similarity. It's basically a measure of the angle between those two vectors in that high-dimensional space.
Right, closer to 1 means more aligned, closer to 0 means less aligned.
Exactly. So during training, the objective is simple. Maximize the cosine similarity for the n correct image-text pairs in the match.
And minimize it for all the wrong ones.
Precisely. Minimize the cosine similarity for those n squared minus n incorrect pairs.
And how do you optimize that? What kind of loss function do you use?
They use what's called a symmetric cross-entropy loss over all those similarity scores. It's closely related to other contrastive losses you might hear about, like InfoNCE, which stands for noise contrastive estimation.
InfoNC. Okay, what's the intuition there?
Think of it like this. InfoNC pushes the model to make sure that the vector for the correct image contains the maximum possible information about its true text partner compared to all the other noise text vectors floating around in the batch.
So it's not just saying this is the best match, it's saying this is the only plausible match,
Yeah.
and all the others are clearly wrong.
Yeah, it encourages a really strong separation. It wants the score for the correct pair to be dramatically higher than the scores for the incorrect pairs.
That sounds like it needs careful tuning. You mentioned this temperature parameter, tau. Is that involved here?
Absolutely crucial. The temperature is a small number they actually learn during training. It basically scales those raw cosine similarity scores before you calculate the probabilities using softmax.
Okay, so what does scaling them do?
Think of it like adjusting the sharpness or strictness of the scoring. A lower temperature makes the probability distribution sharper. It forces the model to be really confident and assign almost all the probability mass to the single correct pairing.
Penalizing uncertainty heavily.
Right? A higher temperature softens things out. Finding the right temperature and letting the model tune it itself is key to making the training stable and effective across those millions and millions of pairs.
Got it. Okay, let's switch gears slightly to the architectures. What are these image and text encoders actually made of? What's under the hood?
For the text encoder, they used a pretty standard transformer architecture, based on earlier work from Radford and others at OpenAI.
Okay, the standard building block for language now.
Right. A key detail, though. They took the final text representation, the embedding vector, from the activations at the very last token in the sequence, the special EOS or end of sequence token.
Interesting. And did they find they needed a huge text model?
That was one of the interesting findings. Performance wasn't super sensitive to the depth of the text encoder, so to save compute, they mainly focused on scaling up the width of the text transformer, kind of in proportion to whatever image model they were using alongside it.
Okay, so what about the image encoder? What were they using for vision?
They tried a couple of things. High-performing convolutional networks, specifically ResNet variants. They incorporated some known improvements, often called ResNet-D, which tweak things like pooling.
And
And crucially, they replaced the standard final step of global average pooling with an attention pooling mechanism.
attention again. So instead of just averaging features across the image.
The model learns where in the image it should focus its attention to generate the final image vector. It can learn that for the text, a dog catching a frisbee, maybe the dog and the frisbee regions are more important than the background grass.
That makes a lot of sense, especially with messy web images where the subject might be small or off-center.
Exactly. It adds a layer of learned relevance. And they also tested the vision transformer, the VIT, which was newer at the time.
Right, applying the transformer idea directly to image patches.
Both approaches, the attention-pooled ResNets and the VITs, worked well.
Okay, so we've got the scale, the contrastive learning breakthrough, the math with cosine similarity, and InfoNC, the architectures. Now the big payoff, zero-shot transfer. How good was it really?
This is where it gets genuinely impressive. Previous attempts at zero-shot image classification, like a system called visual engrams, were getting maybe 11.5% accuracy on ImageNet, kind of a proof of concept.
Okay, 11.5%. And CLIP?
CLIP's best model hit 76.2% zero-shot accuracy on ImageNet.
76%. Zero shot.
Zero shot, meaning it had never seen a single labeled ImageNet example during training. It just used its general knowledge learned from the web text and images.
And put that 76.2% in context.
That number matched the accuracy of the original ResNet 50 model.
Which was trained specifically on ImageNet.
Exactly. Trained on 1.28 million labeled ImageNet examples, CLIP got there with 0 labels for those specific classes just by understanding language descriptions.
That's incredible. And the way it does the classification is just so elegant. You don't train a new classifier layer.
Yep.
The text encoder becomes the classifier generator. You just feed it the names of the classes you care about.
That's the beauty of it. You want to classify dog versus cat versus bicycle. You run the text, a photo of a dog, a photo of a cat, a photo of a bicycle, through the text encoder. That gives you 3 text vectors.
Your classifier waits, essentially, in the shared space.
Exactly. Then you take your image, run it through the image encoder to get its vector, and you just see which text vector it's closest to using cosine similarity. Whichever text matches best, that's your predicted class. It's like a hypernetwork generating the classifier on the fly from language.
It wasn't quite that simple in practice initially, was it? There was a wrinkle with just using single words.
Yes. The ambiguity of language. Polysemy. The classic example is crane.
Bird or construction equipment.
Right. Because CLIP was trained on full sentences from the web, a crane lifting steel beams, a white crane standing in the water. Just giving the text encoder the single word crane was confusing. The resulting vector was probably some weird average of the bird and the machine concept.
So the raw word embedding wasn't specific enough because it lacked the context the model learned during pre-training.
Yes, exactly.
And the solution became what we now call prompt engineering.
Yep. A term that barely existed then but is everywhere now. They realized they needed to give the model that sentence-like context it was used to.
So instead of just crane?
They tried wrapping it in a template, like a photo of a label. So, a photo of a crane.
And did that help?
It made a real difference. Just using that simple template boosted the ImageNet zero-shot accuracy by 1.3%. Free performance just by tweaking the input text slightly.
Wow. And they didn't stop there, right? They did ensembling.
Yeah, they realized different phrasing might capture different nuances, so they tried using multiple prompts for the same label, maybe a photo of a big label, a photo of a small label, a photo of a label in the wild, things like that.
And then average the results.
Average the similarity scores you get from the resulting text vectors. And that ensemble of different prompts gave them another 3.5% accuracy boost.
So that's almost 5% total improvement just from clever prompting. No model retraining, no new image data.
Exactly. It really highlights how intertwined the language understanding is with the visual representation. Context matters.
It's a fantastic insight. Okay, so wrapping things up a bit. The core magic of CLIP seems to be this combination. Massive, massive scale, that 400 million pairs, coupled with a really simple, efficient, contrastive learning goal.
And that combination created these powerful, jointly embedded image and text representations.
Which led to that amazing zero-shot capability.
And also, interestingly, much better robustness. This was a key finding. Because CLIP learned from such diverse, noisy web data, it didn't overfeed to the specific quirks of one clean dataset like ImageNet.
So it generalizes better not just to new classes, but to slightly different styles of images too, like distribution shifts.
Exactly. It held up much better when tested on images that were slightly different from the standard benchmarks, different lighting, poses, contexts. It suggests that this kind of zero-shot evaluation might be a more sort of honest measure of a model's real-world capability than just testing on the same distribution it was trained on.
That's a really important point for thinking about how we evaluate AI. Still, even with all this power, CLIP isn't perfect, right? They pointed out limitations.
Oh, definitely. For all its breadth, it struggles with tasks that require really fine-grained distinctions or understanding things that are very abstract or very different from typical web images.
Like the example they gave with handwritten digits.
Yeah, M-nice digits. Simple black and white handwritten numbers. Zero-shot CLIP actually performs pretty poorly on that. A basic logistic regression model trained directly on the pixel values does better.
Which is kind of wild. It shows there's still a gap. This broad web-scale knowledge doesn't automatically translate to every single specific, perhaps simpler visual task.
It's the core tension, isn't it? We have CLIP's amazing generalization from massive data, but humans, even children, can learn completely new concepts, sometimes very abstract ones, from just a handful of examples.
That few-shot learning ability is still the gold standard.
Right. So the next big leap probably isn't just more data, but finding algorithms that can combine CLIP's kind of broad world knowledge with that human-like efficiency for learning truly novel things, deep conceptual understanding from limited exposure.
That really is the frontier. So here's something for you, the listener, to think about. Given that CLIP learns from image-text pairs found online, what's a visual concept that humans universally understand, but that would be incredibly difficult, maybe impossible, to capture accurately for CLIP using just a short, unambiguous sentence prompt? Something visual that provides easy description. Lots to chew on there. That's all the time we have for this deep dive. Thanks for joining us.